Week 13, Tuesday. Today our agenda will be on von Mises criteria, which is another criteria that we'll learn. And this criteria is based on maximum distortion energy. Then I'm going to do a long example on combined loading. Okay. But before we go on, I want to quickly recap, review the maximum shear stress criteria. For this case, what I'm talking about is Tresca criteria. So if we were to look in Tresca criteria, and if we have a 3D element, so this is X, Y, and Z, and then this is our element over here. And our element happen to be under a load that is stress X, okay? And we will label this as our point X. This is our point Y, and this is our point Z. And on the element that just sketched, we know that stress Y is equal to normal stress Z is equal to 0. And we know all the shear component. They're all equal to 0. And then when this is the case, when we were to sketch out a 3D mole circle, right? If we were to sketch 3D mole circle, right? So we know that this is our normal stress, shearing stress, element rotate clockwise, element rotate clockwise. And then we have our normal stress Z, normal stress X over here, line. This is our normal stress Y, and normal stress Z is equal to 0. So we know that over here, this is our point X, and our point Y and point Z are at the same point. And then we can draw a circle. And this single circle represents all three planes. Okay. So this circle that you see down here represent the all three planes. So this belongs to our XY plane. This circle is also belongs to our XZ plane, and it also belongs to our XZ plane. Okay. So when that's the case, when we were to compute tau max, okay, so if we were to calculate tau max, it's very straightforward. It's just basically equal to stress X divided by 2. Okay. Now, however, if we have, so now this element is the first element that I've drawn is oriented in its principal plane. So shear stress is equal to 0. Okay. Now, in reality, we always realize that that's not always the case. So again, based on this transformation, this is our X, Y, and then this is our Z. Usually, which I will show you more examples on this over the next few lectures or last 2 lectures. we usually have a shear component. Okay, we usually have a shear component, and this is our shear XY. It's got shear YX. Okay, so this is the most commonly loading of elements in 3D. Okay, so when that's the case, when now we were to sketch Mohs circle, okay, so again, we label this as X, we label this as Y, and we label this as point Z. Okay, so when we sketch our Mohs circle, let me bring it down slightly. So when we sketch our 3D Mohs circle, right, it looks different. Right, so this is our normal stress, zeroing stress element rotate clockwise, zeroing stress element rotate anti-clockwise. Then it usually looks like this. Okay, so let me draw the first circle first, the biggest circle first. Okay, so this is one of the circle, right? Then we know that over here, this is our point Z, right? And then we have one circle over here. And then we have another circle. No, sorry, it should not. Hold on. I have to shift this slightly. Okay, so this is right. This is one of our circle. Then we have another circle. I do apologize. So 2, 4, 6, 8. We have another circle over here. Wait, how come now my circle are not round? Hold on. Yeah, that's why. We have one circle over here. Let me shift it. Oh no, it looks weird. Okay. Hold on. Something in my head is not making sense. Hold on. I do back. Let me draw it properly, okay? I'm trying to skip steps. That's where my problem comes. So when we have a circle on this configuration, let me sketch this out properly rather than. So we know that we have a shearing stress. And we know that we have a shearing stress. And then we know that we have a normal stress. Okay, stress Z, not stress X, sorry. So over here, we know that, oh, this is our element rotating anti-clockwise. So this is our point X. And over here, this is our point Y. So now we can draw a circle. And this circle center. Hold on. Let me draw where the stress average is first. So if this is our stress average line, and then I can construct a circle. we know that this circle belongs to our XY plane. And I can now sketch a line. And then come the other two circles. One is here. And the other one is here. And we know that the red circle belongs to the XZ plane. And this one, the smallest one, belongs to the YZ plane. And when that's the case, when there's a situation like this, right, we know that this is our stress max. Over here, this is our stress mean, right? So when you have a circle in this situation, after sketching 3D mold circle, then your maximum shear stress criteria changes. The formula changes. You know that stress max is equal, shear max is equal to stress max minus stress mean divided by 2. And we are aware to calculate stress max and mean. First of all, we need to find the center of circle. So center of circle is known as the average stress. So while using the circle that we've just, the 3D mold circle we've done, we know that stress X plus by stress Y divided by 2. Okay. And then we were to find the radius of the circle. Why we need to find a radius of the circle? Because stress max and stress mean is equal to stress average plus by minus by tau max, which is the radius of the circle. So radius of circle, which is equal to our tau max. So this will be equal to our stress X plus by normal stress Y divided by 2 squared plus by shear XY squared. Okay. So from here, we can find our stress max and mean. Which is equal, I've written out before, stress average plus or minus by tau max. Okay. So we know that the maximum shear is equal to the value of stress max minus by stress mean divided by 2. Now, some of you might be confused. This stress max is a material property. Okay. This tau max is due to loading. Okay, so don't be confused. So this will be equal to stress average plus by tau max minus by stress average minus by tau max, because it's a minimum value. Okay, then you divide by 2. And then you divide by 2. And this happened to be equal to tau max also. Right? This happened to be equal to tau max. Now, this tau max over here is due to loading. Okay. This is due to material property. Okay. So i.e. this is from experiment. Okay. This one is from analysis or calculation. Okay. Right. So this is just a quick review on what we learned on maximum shear stress, most important thing you have to know, like what I keep on